Welcome back to Nebula Nights, where we explore the cosmos in ways that bring the universe closer to home. Tonight, we're embarking on a rather morbid but fascinating thought experiment. Imagine standing on the surface of another world without the protection of a spacesuit. How long would you last? What would kill you first? Would it be the searing heat, the bone-chilling cold, the crushing pressure, or simply the absence of air to breathe? For millennia, humans have gazed up at the night sky and wondered what it would be like to walk on other worlds. Our ancestors saw wandering stars and wove stories about gods and heroes. Today, we know these points of light are planets, entire worlds with their own unique characteristics, atmospheres, and hostile environments. While our robotic emissaries have touched down on Mars, plunged into Jupiter's clouds, and skimmed past the ice giants at the edge of our solar system, humans remain confined to Earth and brief ventures to our moon. But let's imagine, just for tonight, that you could magically appear on any planet in our solar system. No spacecraft, no protective gear, just you in whatever clothes you're wearing right now. How would each world greet you? The answer varies dramatically depending on where you land, and the results might surprise you. Some planets would end your existence in a fraction of a second, while others might grant you precious minutes to contemplate your surroundings before the inevitable overtakes you. Before we begin our tour of the solar system's most hostile environments, we need to understand what happens to the human body when it's exposed to conditions far outside the narrow band of survivability we've evolved to inhabit. Your body is an incredibly complex machine, finely tuned over millions of years of evolution to function within specific parameters. Remove those parameters and systems begin to fail in predictable, often rapid ways. The human body requires three fundamental things to survive: oxygen to fuel our cells, pressure to keep our fluids in their proper state, and temperatures within a range that doesn't destroy our proteins and cellular structures. On Earth, at sea level, we experience an atmospheric pressure of approximately 101.3 kilopascals, or 1 atmosphere. This pressure is what keeps water in your body liquid at normal body temperature. It's what allows oxygen to transfer from your lungs into your bloodstream. It's what prevents the dissolved gases in your blood from forming bubbles. There exists a critical threshold known as the Armstrong limit, named after United States Air Force General Harry George Armstrong, who identified this boundary in the late 1940s. This limit occurs at an altitude of approximately 19 kilometers, or about 63,000 feet above sea level, where the atmospheric pressure drops to 6.3 kilopascals. At this pressure, something remarkable and terrifying happens. Water begins to boil at normal human body, temperature of 37 degrees Celsius. If you are exposed to pressures at or below the Armstrong limit, the moisture on your tongue, in your eyes, and on the surface of your lungs would begin to vaporize. This phenomenon is called ebullition, from the Latin word ebullire, meaning to bubble out or boil up. Your tissues would swell as water vapor and dissolved gases form bubbles throughout your body. In a 1966 accident at NASA's Johnson Space Center, a technician named Jim LeBlanc was accidentally exposed to near vacuum conditions when his spacesuit lost pressure during testing. He later recalled that his last conscious memory before passing out was feeling the saliva on his tongue beginning to boil. Fortunately, the chamber was repressurized within seconds, and he survived without permanent injury. The timeline for surviving vacuum exposure is brutally short. Within 10 to 15 seconds, you would lose consciousness as oxygen is pulled from your lungs and bloodstream. Your blood itself wouldn't boil, protected as it is within your circulatory system, but you'd have between 60 and 90 seconds before death becomes inevitable, assuming pressure could be restored. Without repressurization, the combination of hypoxia, lack of oxygen to the brain, and the tissue damage from ebullition would kill you within 2 minutes at most. But vacuum isn't the only way to die in space. Temperature extremes, toxic atmospheres, and crushing pressures each present their own unique threats. Some planets kill through multiple mechanisms simultaneously, while others have a clear primary cause of death. As we journey through our solar system tonight, keep in mind that we're not just cataloging the ways these worlds can kill us, but exploring the remarkable diversity of planetary environments and what makes Earth so extraordinarily special. So settle in, dim the lights, and let's begin our journey at the scorched inner edge of our solar system, where the sun's fury creates one of the most temperature-extreme worlds we know. Our journey begins with Mercury, the smallest planet and the closest to the sun. This diminutive world, barely larger than Earth's moon, presents one of the most extreme dichotomies in the solar system. Mercury is a planet of absolutes, where one side bakes under the relentless glare of a sun 7 times brighter than what we experience on Earth, while the other side plunges into darkness and cold that would freeze carbon dioxide solid. Picture yourself materializing on Mercury's surface. The first thing you'd notice if you appeared on the day side is the sun. It would dominate nearly a third of the sky, a bloated, angry sphere pumping out radiation with terrifying intensity. Mercury has no atmosphere to speak of, just trace amounts of atoms kicked up from the surface by the solar wind and micrometeorite impacts. This means there's no air to breathe, no protective blanket to shield you from the sun's radiation, and no medium to moderate the temperature extremes. If you had the misfortune to appear on the sunlit hemisphere, your fate would be sealed in seconds. The daytime temperature on Mercury reaches approximately 430 degrees Celsius or over 800 degrees Fahrenheit. To put this in perspective, this temperature exceeds the melting points of lead, tin, and zinc. Any exposed skin would begin to char and burn almost instantly. The fabrics of your clothing would likely ignite, and you'd become a human torch within moments. You might survive for 30 seconds, perhaps 45 if you were extraordinarily lucky, but the thermal radiation alone would cause fatal burns across your entire body long before asphyxiation could claim you. On the night side of Mercury, the scenario is entirely different but equally deadly. Here, temperatures plummet to approximately negative 180 degrees Celsius or negative 290 degrees Fahrenheit. This is colder than the coldest temperatures ever recorded on Earth, colder than the ice caps of Antarctica, cold enough to freeze carbon dioxide into dry ice. Exposed to these temperatures, you would begin to experience severe frostbite within seconds. Your extremities would freeze first, fingers and toes losing circulation as blood vessels constrict in a futile attempt to preserve core body temperature. But without atmosphere and without a heat source, your core temperature would drop catastrophically fast. Here's where Mercury becomes interesting from a survival standpoint. The planet rotates extremely slowly, taking 58 Earth days to complete one rotation. This means that between the day and night sides, there exists a twilight zone, a region known as the Terminator, where temperatures are potentially more moderate. Some scientists have calculated that if you could position yourself right at this boundary and somehow rotate like a rotisserie chicken, continuously turning to expose all sides of your body equally to the heat and cold, you might be able to maintain a survivable body temperature. But here's the critical factor. Even in this theoretical sweet spot, you're still contending with the complete absence of atmosphere. Mercury's atmospheric pressure is essentially zero, far below the Armstrong limit. This means ebulism would begin immediately. The moisture on your tongue and in your eyes would start to boil. More critically, your lungs would be unable to hold oxygen. If you tried to hold your breath, the air in your lungs would expand violently as the pressure differential between the inside of your body and the outside environment sought to equalize. This would rupture your alveoli, the tiny air sacs in your lungs where gas exchange occurs, causing them to tear and bleed. The smarter strategy, counterintuitive though it might seem, would be to exhale and not try to hold your breath. This would give you those precious extra seconds. As the oxygen in your bloodstream depletes, you'd experience the effects of hypoxia. Your vision would narrow, a phenomenon called tunnel vision, as your peripheral vision fails first. You'd feel lightheaded, confused, perhaps euphoric as your brain cells begin to misfire without adequate oxygen. Within 10 to 15 seconds, you'd lose consciousness. Your heart would continue to beat for perhaps another 30 to 60 seconds, but without oxygen, brain death would occur quickly. So even in the best-case scenario on Mercury, positioned at the Terminator and avoiding both the worst of the heat and cold, you might survive for approximately 2 minutes. This assumes you don't panic, that you exhale immediately to prevent lung rupture, and that your body can withstand the swelling and tissue damage from ebulism long enough for your oxygen reserves to be depleted. In reality, most people would likely lose consciousness within 60 seconds and be dead within 90. It's worth noting that Mercury's weak gravitational field, about 38% of Earth's, means you'd feel lighter, able to jump higher. But this is cold comfort when you have seconds to live. The lack of atmosphere also means you'd be exposed to the full spectrum of solar radiation, including ultraviolet, X-rays, and gamma rays. While this wouldn't kill you as quickly as the pressure or temperature extremes, if somehow you could survive everything else, you'd receive a lethal dose of radiation within minutes. Mercury teaches us our first lesson about planetary survival. Temperature extremes alone aren't necessarily the limiting factor. Even if you could somehow manage the heat or cold, the absence of breathable atmosphere and adequate pressure will kill you quickly. But as we'll see, Mercury is actually one of the more survivable planets when compared to our next destination, a world that makes Mercury look positively hospitable by comparison. If Mercury is the solar system's furnace, then Venus is its pressure cooker. Often called Earth's twin because of its similar size and mass, Venus is anything but familiar when it comes to surface conditions. This planet, shrouded in beautiful, pearlescent clouds that make it the brightest object in our night sky after the moon, hides beneath those clouds one of the most hellish environments imaginable. Let's paint the picture of what awaits you on Venus. Imagine materializing on the surface, and immediately, before you can even draw a breath, you're subjected to 3 simultaneous killing mechanisms, each one independently capable of ending your life in moments. Venus doesn't just kill you, it obliterates you through multiple overlapping means. First, there's the pressure. The atmosphere of Venus is incredibly thick, composed of 96% carbon dioxide. The pressure at the surface is 92 times that of Earth at sea level. To understand what this means for your body, imagine being approximately 900 meters, or nearly 3,000 feet, underwater in Earth's oceans. That's the equivalent pressure you'd experience standing on Venus's surface. This pressure would be immediately transmitted through your body, compressing your entire frame. Your soft tissues would compress, your chest would be crushed, making it impossible to expand your lungs even if there were oxygen to breathe. The pressure would force its way into your sinuses, your middle ear, causing them to collapse or rupture. But you wouldn't have time to process these sensations because the second killing mechanism would already be at work. The temperature on Venus's surface averages around 737 Kelvin or 464 degrees Celsius, which is 867 degrees Fahrenheit. This temperature is hotter than the surface of Mercury, despite Venus being nearly twice as far from the Sun. The reason for this incredible heat is Venus's runaway greenhouse effect. The thick carbon dioxide atmosphere traps solar radiation with extraordinary efficiency, heating the surface to temperatures that exceed the melting points of lead at 600 degrees Celsius, tin at 232 degrees Celsius, and zinc at 420 degrees Celsius. At these temperatures, the very proteins that make up your body would begin to denature, to break down and lose their structure. Your skin wouldn't just burn, it would char and potentially ignite. The fatty tissues beneath your skin would begin to melt. Your eyes would cook in their sockets. The thermal damage would be so rapid and so total that nerve endings would be destroyed before they could even transmit pain signals to your brain. In effect, you'd be simultaneously cooked and compressed. But wait, there's more. The atmosphere you're being crushed and cooked in isn't just carbon dioxide. Venus's clouds are composed primarily of sulfuric acid. That's right, concentrated sulfuric acid droplets floating in the atmosphere. While you'd be dead long before the acid could do significant damage compared to the heat and pressure, it adds insult to fatal injury. Any exposed surfaces would be subjected to one of the most corrosive substances known to chemistry. So, how long would you survive on Venus? The answer is measured not in minutes or even tens of seconds, but in less than 1 second. The combination of crushing pressure and extreme heat would incapacitate you effectively instantaneously. Your body would be compressed, cooked, and crushed before you could even process what was happening. If we're being generous and assuming your final neural signals could propagate through rapidly dying brain tissue, you might maintain some form of consciousness for perhaps 2 to 3 seconds. But any meaningful survival time is effectively zero. Let's dig deeper into what the atmosphere of Venus really means. At 92 times Earth's atmospheric pressure, the carbon dioxide at the surface is technically not even a gas. Extreme pressure is uniquely deadly. You couldn't survive long enough to appreciate the surreal landscape around you, the volcanic plains, the mountain ranges taller than anything on Earth, or the fact that Venus's clouds reflect so much sunlight that the surface is illuminated by a diffuse, orange-tinted glow. From Venus, we move to the only place in the known universe where life thrives, where the conditions are so perfectly balanced that complex organisms can exist, evolve, and contemplate their own existence. We return home, to Earth. After discussing the hellish conditions of Venus and Mercury, arriving at Earth feels like stepping into paradise. And in many ways, it is. Earth is the only known planet in the universe where you can stand on the surface without a spacesuit and not immediately die. This might seem like an obvious statement, but when you consider the sheer number of ways planetary environments can be hostile to life, the fact that Earth is so accommodating becomes extraordinary. What makes Earth special? Let's start with the atmosphere. Earth's atmosphere is approximately 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition is not coincidental. It's the result of billions of years of geological and biological processes. The oxygen we breathe is primarily a product of photosynthesis, generated by plants, algae, and cyanobacteria over eons. Early Earth had almost no free oxygen. Its appearance in significant quantities marked one of the most dramatic transformations in our planet's history. The atmospheric pressure at Earth's surface averages 101.3 kilopascals, or 1 atmosphere. This pressure is perfect for keeping water in its liquid state across a wide range of temperatures. Water can exist as ice at the poles, as liquid in our oceans and rivers, and as vapor in our air. This triple point of water, where all three phases can coexist, is crucial for Earth's climate system and for life itself. Earth's temperature range is remarkably moderate compared to other planets. The average surface temperature is about 15 degrees Celsius or 59 degrees Fahrenheit. Of course, this varies widely depending on location and time of year. The coldest temperature ever recorded on Earth was negative 89.2 degrees Celsius at Antarctica's Vostok Station, while the hottest was 56.7 degrees Celsius in California's Death Valley. But even these extremes are within the range where humans can survive, at least temporarily, with appropriate shelter and preparation. One of Earth's most important features is its magnetic field, generated by the motion of molten iron in the planet's outer core. This magnetic field extends far into space, creating the magnetosphere that deflects most of the solar wind and cosmic radiation that would otherwise strip away our atmosphere and bombard the surface. Without this protective bubble, Earth would gradually lose its atmosphere to space, as Mars likely did billions of years ago. Earth's position in the solar system, often described as being in the Goldilocks zone or habitable zone, is another key factor. We orbit at approximately 1 astronomical unit from the Sun, or about 150 million kilometers. At this distance, we receive enough solar energy to keep the surface warm enough for liquid water, but not so much that water boils away. Move Earth closer to the Sun, perhaps to Venus's orbit, and we'd experience a runaway greenhouse effect. Move it farther out, perhaps to Mars's orbit, and much of our water would freeze. The presence of liquid water on Earth's surface is perhaps the single most important factor for life as we know it. Water is an extraordinary solvent, capable of dissolving and transporting nutrients and minerals. It has unusual properties, like being less dense as a solid than as a liquid, which means ice floats and insulates the water below, allowing aquatic life to survive through winter. The water cycle, driven by solar energy, distributes heat and moisture around the planet, moderating climate and making diverse ecosystems possible. Earth's geology plays a crucial role in maintaining habitable conditions. The process of plate tectonics, where large sections of Earth's crust move and interact, creates mountains, volcanic activity, and the recycling of materials between the surface and the interior. This geological activity is part of Earth's carbon cycle, which regulates the amount of carbon dioxide in the atmosphere over long time scales, preventing runaway greenhouse effects or ice ages. But let's bring this back to our thought experiment. On Earth, you can stand outside without a spacesuit and survive indefinitely, limited only by your need for food, water, and shelter. In most locations and most times of year, you can survive at least several days without these essentials. Even in Earth's harshest environments, the Antarctic or the Sahara, survival is measured in hours to days, not seconds or minutes. This is what makes Earth unique in our solar system. Every other planetary body presents immediate, acute threats that will kill you in timescales ranging from a fraction of a second to a few minutes. Only on Earth can you stand unprotected and contemplate your surroundings, feel the breeze, watch the clouds, and know that the environment itself isn't actively trying to kill you. Of course, Earth isn't without its dangers. Extreme weather events, wildlife, lack of potable water in some regions, and human-caused hazards all present risks. But these are categorically different from the instant lethality of Venus's surface or the rapid asphyxiation you'd experience on Mars. On Earth, the environment provides what you need to survive, and with knowledge and preparation, humans have managed to inhabit almost every corner of the planet, from the Arctic to the tropics, from high mountains to sea level. As we leave Earth and venture to the outer planets, we'll see that conditions become colder and, in many ways, even more alien. Our next stop is Mars, the planet that has captured human imagination as the most likely candidate for future exploration and even colonization. Mars has long been the focus of human fascination. From Percival Lowell's mistaken observations of canals to the Viking landers, and now sophisticated rovers like Curiosity and Perseverance, we've studied Mars more than any other planet except Earth. It's been the setting for countless science fiction stories, and serious scientists and engineers have drawn up plans for eventual human missions. But strip away the romance and the dreams of terraforming, and you find a world that, while less immediately lethal than Venus or Mercury, is still profoundly hostile to unprotected human life. Landing on Mars without a spacesuit, you'd find yourself in an environment superficially more familiar than what you'd encounter on Mercury or Venus. The landscape might resemble a desert on Earth, with rust-colored soil and rocks stretching to the horizon. The sky would be a butterscotch or salmon color during the day, tinted by dust suspended in the thin atmosphere. You might even see clouds, wispy ice crystal formations made of water or carbon dioxide. But this familiarity would be deceptive. Mars is trying to kill you, just more slowly than the inner planets. The first thing you'd notice is the cold. Mars is the fourth planet from the Sun, significantly farther out than Earth, and it receives only about 43% of the solar energy we do. The average surface temperature is around -63 degrees Celsius or -81 degrees Fahrenheit. However, Mars experiences substantial temperature variations. Near the equator on a summer day, temperatures might climb to around 20 degrees Celsius or 70 degrees Fahrenheit. That's actually pleasant by Earth standards. But at night, temperatures can plummet to -100 degrees Celsius or even colder. At the poles during winter, it can reach -140 degrees Celsius or -220 degrees Fahrenheit. So depending on where and when you appeared on Mars, the temperature might be manageable for a while. If you materialize near the equator at midday, you might not immediately freeze. In fact, if you were wearing suitable cold weather clothing, you could potentially avoid hypothermia for several minutes to even an hour. But temperature isn't what would kill you on Mars. The atmosphere would. Mars's atmosphere is extremely thin, with a surface pressure averaging only 610 pascals, or about 0.6% of Earth's atmospheric pressure. This is well below the Armstrong limit. At this pressure, water boils at approximately 2 degrees Celsius. Your body temperature is 37 degrees Celsius. This means that ebullition would begin immediately. The composition of Mars's atmosphere is also problematic. It's approximately 95% carbon dioxide with about 3% nitrogen, 1.6% argon, and only trace amounts of oxygen. Even if the pressure were adequate, you couldn't breathe this atmosphere. The carbon dioxide concentration alone would be toxic, and the lack of oxygen would quickly lead to hypoxia. So here's what would happen if you appeared on Mars without a spacesuit. As the extremely low pressure hits you, the moisture on your tongue and eyes would begin to vaporize. You'd feel an intense cooling sensation as the evaporative cooling occurred, similar to how sweating cools you on Earth, but far more extreme. Your soft tissues would begin to swell as water vapor and gases came out of solution in your body. At the same time, the lack of oxygen would begin to take its toll. With each attempted breath, you'd be drawing in mostly carbon dioxide at a pressure too low to sustain life. The carbon dioxide would actually begin to diffuse into your bloodstream faster than your body could expel it, leading to hypercapnia or carbon dioxide toxicity. This would cause severe acidosis in your blood, interfering with cellular function. You'd become hypoxic very quickly. The oxygen in your blood would be depleted in seconds. Within 15 to 30 seconds, you'd feel dizzy and confused. Your vision would begin to narrow. By 45 seconds to a minute, you'd lose consciousness. Unlike the instant death you'd experience on Venus, or even the rapid death on Mercury, on Mars you'd have about a minute of consciousness, and your heart might continue to beat for another minute or two beyond that. So total survival time on Mars without a suit, from appearance to death, would be approximately 2 to 3 minutes. This is actually longer than Mercury in most cases, and vastly longer than Venus. The reason Mars grants you a bit more time is that while the pressure is too low to sustain life, it's not quite vacuum. There's enough atmosphere to slightly slow the ebulism process compared to hard vacuum. The temperature, if you appeared at a favorable time and place, might not immediately cause tissue damage. Your death would primarily be from asphyxiation, rather than from the more rapid causes we saw on the inner planets. Interestingly, if you could somehow breathe on Mars, if someone handed you a tank of pressurized oxygen and a mask, you'd face another problem: the lack of adequate pressure for normal respiration. At Mars's surface pressure, you'd need a pressure suit or a pressurized environment. Just having oxygen available isn't enough. It needs to be delivered at a pressure sufficient for your lungs to extract it efficiently. Mars also presents hazards beyond temperature and atmosphere. The planet has massive dust storms that can engulf the entire planet for weeks or months. These storms can reduce solar energy reaching the surface. What happens if you somehow appear at Jupiter? The concept is tricky because there's no distinct boundary where the planet begins. But let's say you appear at the level where the atmospheric pressure equals 1 bar, the same as Earth's sea level pressure. This is the conventional surface that scientists use when describing the visible features of Jupiter. At this level, the temperature is already around negative 150 degrees Celsius or negative 240 degrees Fahrenheit. The atmosphere is about 90% hydrogen and 10% helium by volume. There's no oxygen to breathe. But the temperature and lack of oxygen are the least of your problems. As you appear at Jupiter's 1 bar level, you'd immediately begin to fall. Jupiter's gravity is about 2.5 times Earth's, so you'd accelerate downward at roughly 25 meters per second squared. As you fall, the pressure and temperature would increase rapidly. Unlike Earth, where you can only fall to the ground, on Jupiter you'd keep falling deeper into increasingly hostile conditions. Within seconds of appearing, the crushing pressure would begin to affect you. By the time you fall into the 2 bar level, just kilometers below where you started, the pressure would already be twice what you're used to. Your lungs would be unable to expand against the external pressure. By the 10 bar level, reached in perhaps 30 seconds of falling, the pressure would be equivalent to being 100 meters underwater on Earth. Your ribs would crack, your organs would be compressed, and you'd likely lose consciousness from the combination of pressure trauma and hypoxia. But you'd keep falling. As you descend deeper into Jupiter, the temperature rises dramatically. The planet generates more heat than it receives from the Sun, a remnant of gravitational compression from its formation. Deep in Jupiter's interior, temperatures reach tens of thousands of degrees Celsius. The pressure becomes millions of times Earth's atmospheric pressure. At these depths, hydrogen itself transitions into exotic states, eventually becoming metallic hydrogen, a liquid form that conducts electricity and is thought to generate Jupiter's powerful magnetic field. Of course, you'd never witness these deep layers. Within the first minute of appearing at Jupiter, you'd be rendered unconscious by the pressure. Within 2 minutes, you'd be dead, your body crushed by the ever-increasing pressure as you plummet through the atmosphere. As you continue to fall, your remains would be compressed further and further, eventually heated to the point of complete molecular disintegration. The survival time on Jupiter is therefore similar to Mars in terms of consciousness, around 1 minute, but the mechanism is entirely different. On Mars, you die from asphyxiation and pressure too low. On Jupiter, you die from crushing pressure that's too high. Both environments kill you in approximately the same time frame, but the experiences would be vastly different. Jupiter's atmosphere is also incredibly violent. Wind speeds in the bands and zones we see from space can exceed 360 kilometers per hour or 224 miles per hour. The Great Red Spot, a storm larger than Earth itself, features winds exceeding 430 kilometers per hour. These aren't gentle breezes. These are winds powerful enough to tear apart anything in their path. If you appeared in or near one of Jupiter's storms, the winds alone could potentially dismember you even before the pressure crushed you. Another fascinating and terrifying aspect of Jupiter is its radiation environment. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. This magnetic field traps charged particles, creating radiation belts far more intense than Earth's Van Allen belts. The radiation levels near Jupiter are lethal to unprotected humans within hours to days. Near some of Jupiter's inner moons, like Io, radiation doses can be fatal in minutes. But again, this is irrelevant if you're falling through Jupiter's atmosphere without protection. You'd be dead from pressure long before radiation could harm you. The radiation is more of a concern for spacecraft and any future missions to Jupiter's moons. Jupiter also has lightning, but not the kind we're familiar with. Jovian lightning is far more powerful than Earth's, with some bolts calculated to be up to 3 times more powerful than the strongest lightning on Earth. These bolts originate deep in the atmosphere, in the water cloud layer, and can be detected from space. If you happen to appear in the path of one of these tremendous electrical discharges, you'd be vaporized instantly, though this would arguably be more merciful than the slow crushing you'd otherwise experience. One interesting thought experiment is what would happen if you could somehow stop yourself from falling on Jupiter and had a source of oxygen at sufficient pressure. Even then, the cold at the 1 bar level, negative 150 degrees Celsius, would kill you through hypothermia within minutes to hours, depending on your clothing and body mass. The hydrogen-helium atmosphere would be incredibly efficient at conducting heat away from your body. Hydrogen has very high thermal conductivity, which means it would pull heat from your body much faster than Earth's nitrogen-oxygen atmosphere would at the same temperature. Jupiter teaches us that massive size brings its own unique forms of lethality. The crushing pressure of a deep atmosphere, the violent weather systems powered by internal heat, and the lack of any solid refuge make Jupiter profoundly hostile to human life. As we move to Saturn, we'll see similar characteristics, though with some intriguing differences. Saturn, with its magnificent ring system, is perhaps the most visually stunning planet in our solar system. Those rings, composed of countless particles of ice and rock ranging from grain-sized to house-sized, span hundreds of thousands of kilometers, but are sometimes only 10 meters thick. They're a reminder of Saturn's powerful gravitational influence and its system of moons. But the planet itself, beneath those glorious rings, is another gas giant death trap. Saturn is similar to Jupiter in many respects. It's primarily composed of hydrogen and helium. It has no solid surface, and its atmosphere features banded clouds and storm systems. However, Saturn is less massive than Jupiter, and this leads to some important differences in its atmospheric conditions. If you were to appear at Saturn's 1 bar pressure level, the equivalent of Earth's sea level atmospheric pressure, you'd find yourself in an environment around negative 139 degrees Celsius or negative 218 degrees Fahrenheit. This is actually warmer than Jupiter's 1 bar level, despite Saturn being farther from the Sun. The reason is that Saturn, like Jupiter, generates more heat than it receives from the sun, and the balance of internal heat production and solar heating creates these temperature profiles. The atmospheric composition is similar to Jupiter's, about 96% hydrogen and 3% helium by volume, with traces of methane, ammonia, and other compounds. As on Jupiter, there's no oxygen to breathe, and as on Jupiter, you'd begin to fall immediately upon appearing. Saturn's gravity at the 1 bar level is slightly weaker than Earth's, about 1.065 times our surface gravity. This means you'd fall more slowly than on Jupiter, but the outcome would be identical. As you descend, pressure and temperature would increase. You'd lose consciousness within a minute from the combination of hypoxia and increasing pressure trauma. Death would follow within 2 to 3 minutes as the pressure crushed your body. One of Saturn's most famous features is its hexagonal storm at the North Pole. This bizarre geometric storm system spans about 30,000 kilometers across, large enough to fit 4 Earths inside. The hexagon's sides are each longer than Earth's diameter. This hexagonal pattern is thought to be caused by a jet stream interaction, a standing wave pattern in the atmosphere. Wind speeds in this hexagonal jet stream reach about 320 kilometers per hour. At the center of the hexagon is a massive hurricane-like storm, though calling it a hurricane doesn't quite capture its scale. Earth's largest hurricanes are typically a few hundred kilometers across. Saturn's polar storm is 2,000 kilometers wide, and the eye alone is 50 times larger than the eye of a typical Earth hurricane. If you appeared in or near this storm, the violence of the winds would be added to all the other lethal factors. Saturn is also famous for its winds. The equatorial winds on Saturn reach speeds up to 1,800 kilometers per hour, or about 1,100 miles per hour. These are among the fastest planetary winds in the solar system. These supersonic winds create tremendous turbulence and would tear apart anything caught in them. Even accounting for the lower atmospheric density at the 1 bar level compared to deeper in the atmosphere, these winds carry enormous energy. Like Jupiter, Saturn generates significant internal heat, about 2.5 times more energy than it receives from the Sun. This internal heat drives the atmospheric convection and the powerful storm systems we observe. The source of this heat is thought to be helium rain. Deep in Saturn's atmosphere, helium condenses into droplets that fall toward the core, releasing gravitational potential energy as heat through a process similar to how hydroelectric dams generate electricity. As you fall through Saturn's atmosphere, you'd experience this temperature increase. Eventually, many kilometers below the 1 bar level, you'd reach regions where the pressure is thousands of bars and the temperature is thousands of degrees. Your remains would be compressed and heated beyond recognition. Eventually, deep enough in Saturn's interior, conditions become so extreme that hydrogen transitions to metallic hydrogen, just as in Jupiter's core. Saturn's magnetic field is weaker than Jupiter's, but still substantial, about 578 times stronger than Earth's. This creates radiation belts, though not as intense as Jupiter's. The radiation environment around Saturn is hostile to spacecraft and would be harmful to humans over time, but as with Jupiter, you'd be dead from pressure long before radiation became an issue. One unique aspect of Saturn is that it's the least dense planet in the solar system. Its average density is less than that of water, which leads to the often repeated factoid that Saturn would float if you could find an ocean large enough to put it in. This low density is because Saturn's mass is stretched over such a large volume. But don't let this fool you into thinking Saturn is gentle. Low average density doesn't mean low pressure at the levels you'd experience. The pressure still increases dramatically as you descend, and it would still crush you just as effectively as Jupiter would. The rings of Saturn, while beautiful, would present their own hazards if you somehow appeared near them rather than in the atmosphere. The ring particles orbit at high velocities, and impacts with even small particles at those speeds would be devastating. The rings exist in a region of space where tidal forces from Saturn would tear apart any object not held together by its own structural strength. This boundary, called the Roche limit, is why the rings exist at all. Moons or other objects that venture too close to Saturn get torn apart by tidal forces. Surviving at Saturn, then, follows the same grim timeline as Jupiter. Appearance at the 1 bar level, rapid onset of hypoxia and pressure, trauma, unconsciousness within 1 minute, death within 2 to 3 minutes, and complete disintegration of your body as it falls into ever more extreme conditions deeper in the planet. From Saturn, we journey even farther out in the solar system to the ice giants Uranus and Neptune. These planets are different from the gas giants in important ways, and they present their own unique challenges. Uranus is one of the most unusual planets in our solar system. Its most distinctive feature is its extreme axial tilt. While most planets spin roughly upright relative to their orbital plane, Uranus is tilted 98 degrees. This means it essentially rolls along its orbit like a barrel, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of continuous darkness as Uranus completes its 84-year orbit around the Sun. This strange orientation is thought to be the result of a massive collision early in the solar system's history when a large body impacted Uranus and knocked it onto its side. This collision may have also affected Uranus's internal heat generation. Unlike Jupiter and Saturn, Uranus generates relatively little internal heat. It emits only about as much energy as it receives from the Sun, compared to Jupiter's 3 times received energy and Saturn's 2.5 times. Uranus is classified as an ice giant rather than a gas giant. While it still has a substantial atmosphere of hydrogen and helium, approximately 83% hydrogen and 15% helium, it also contains significant amounts of ices. In planetary science, ices refers to volatile compounds like water, methane, and ammonia, which exist in various solid or liquid forms deep in the planet's interior. These ices make up a much larger fraction of Uranus's mass compared to Jupiter or Saturn. If you were to appear at Uranus's 1 bar level, you'd find yourself in a frigid environment. The temperature here is around negative 224 degrees Celsius or negative 371 degrees Fahrenheit. This makes Uranus's upper atmosphere the coldest planetary atmosphere in the solar system. The reason for this extreme cold is the combination of Uranus's distance from the Sun, receiving only about 0.227% of the solar energy that Earth receives, and its lack of internal heat generation. The atmosphere at this level would be a pale blue-green color, tinted by the presence of methane, which absorbs red light and reflects blue and green wavelengths. The view would be eerily serene compared to the churning storms of Jupiter and Saturn. Uranus's cloud features are subtle, making it appear as a relatively featureless blue-green ball when viewed from space. But serene appearance doesn't mean safe. As on the gas giants, you'd begin to fall immediately upon appearing. Uranus's surface gravity is about 0.8 mi6 times Earth's, slightly weaker than our home planet. You'd fall a bit more slowly than on Earth, but the outcome would be the same as on Jupiter and Saturn. The atmospheric composition, mostly hydrogen and helium with some methane, provides no oxygen to breathe. Hypoxia would begin immediately. The extreme cold would start to affect you within seconds. At negative 224 degrees Celsius, frostbite would be essentially instantaneous on any exposed skin. This temperature is far below anything experienced on Earth's surface. It's colder than the coldest temperature ever recorded at Antarctica's Vostok Station, which was negative 89.2 degrees Celsius. At these temperatures, many materials become brittle and fragile. The moisture in your lungs and airways would freeze almost instantly. Your blood, protected inside your body, would take longer to freeze, but the cold would be conducted into your core rapidly. The hydrogen atmosphere would be efficient at pulling heat from your body, just as on Jupiter, perhaps even more so given the extreme temperature differential. You'd lose consciousness within about 1 minute from the combination of hypoxia, extreme cold, and shock. Death would follow within 2 to 3 minutes. As you continue to fall, the pressure would increase, but on Uranus, the pressure increase might actually be somewhat more gradual than on Jupiter or Saturn due to Uranus's lower mass and gravity. Eventually, you'd reach the deeper layers where pressure is thousands or tens of thousands of bars, and temperatures rise to thousands of degrees, but you'd be long dead by then. Uranus has a magnetic field, but it's peculiar. Unlike Earth's magnetic field, which is roughly aligned with the planet's rotation axis, Uranus's magnetic field is tilted 59 degrees from its rotation axis and offset from the planet's center. This creates an asymmetric and wobbly magnetic field as the planet rotates. The cause of this unusual magnetic field configuration isn't fully understood, but it may relate to the fact that the field is generated in a relatively shallow layer within the planet, in the water-ammonia ocean thought to exist deep beneath the visible atmosphere rather than in a deep core as with Earth. Wind speeds on Uranus are substantial but not as extreme as on Jupiter or Saturn. Winds have been measured at up to 250 meters per second or about 900 kilometers per hour, particularly near the equator. These winds would still be powerful enough to cause significant buffeting and could contribute to trauma, though you'd likely be unconscious or dead before the winds could do much additional damage beyond what the cold and pressure would inflict. One interesting aspect of Uranus is that it has seasons, extreme ones given its axial tilt. Currently, we're in a period where Uranus's northern hemisphere is approaching summer solstice, with the North Pole facing the Sun. In this configuration, the Sun appears to circle around the sky above the North Pole, never setting. Hydrogen, 19% helium, and about 1.5% methane. As with Uranus, the methane gives Neptune its distinctive blue color by absorbing red light. But unlike Uranus's relatively bland appearance, Neptune is extremely dynamic. The planet features prominent cloud systems, storms, and the fastest winds in the solar system. Wind speeds on Neptune have been measured at up to 2,160 kilometers per hour, or about 1,340 miles per hour. These are supersonic winds, faster even than Saturn's impressive wind speeds. These extreme winds are thought to be driven by Neptune's internal heat. The energy flowing from the planet's interior creates powerful convection currents that drive the atmospheric circulation. The winds are particularly strong in Neptune's equatorial region and in jet streams at other latitudes. Neptune's most famous storm feature was the Great Dark Spot, discovered by Voyager 2 in 1989. This enormous storm system was roughly the size of Earth and featured winds up to 2,400 kilometers per hour at its edges. The storm was similar in some ways to Jupiter's Great Red Spot, but unlike that centuries-old feature, Neptune's Great Dark Spot disappeared by 1994 when the Hubble Space Telescope looked for it. Since then, other dark spots have appeared and disappeared on Neptune, suggesting that these storms are transient features, unlike Jupiter's persistent Great Red Spot. If you appeared in or near one of Neptune's powerful storms, the winds alone would create tremendous forces on your body. At such high velocities, even Neptune's relatively thin upper atmosphere would exert significant drag and buffeting. You'd be tumbled and tossed violently. While this wouldn't necessarily kill you faster than the cold and lack of oxygen would, it would make your final minute of consciousness considerably more chaotic and disorienting. As with all the giant planets, appearing at Neptune means immediately beginning to fall. Neptune's surface gravity is about 1.14 times Earth's, slightly stronger than our home planet. You'd accelerate downward, encountering increasing pressure and temperature as you descend. The immediate threats are the same as on Uranus: extreme cold and lack of breathable atmosphere. The cold at negative 218 degrees Celsius would cause nearly instant frostbite on exposed skin. The moisture in your eyes, mouth, and respiratory tract would freeze in seconds. Your body would lose heat rapidly to the frigid hydrogen atmosphere. Combined with the immediate onset of hypoxia from the lack of oxygen, you'd lose consciousness within about 1 minute. Death would follow within 2 to 3 minutes as your body's oxygen reserves were depleted and your core temperature plummeted. As you continued to fall deeper into Neptune, you'd encounter the same progression as on the other giant planets: increasing pressure and temperature, eventually reaching regions where pressure measures in thousands of bars and temperatures reach thousands of degrees. Neptune's magnetic field, like Uranus's, is tilted and offset from the planet's center. The field is tilted 47 degrees from the rotation axis and offset by more than half the planet's radius. This creates an asymmetric, complex magnetic field that wobbles as Neptune rotates. The similarity between Uranus's and Neptune's magnetic field configurations suggests this might be a characteristic feature of ice giants, possibly related to how their magnetic fields are generated in the water-rich layers deep within these planets rather than in a central core. Neptune has a ring system, discovered in 1989 by Voyager 2. The rings are thin and dark, similar to Uranus's rings. Some of Neptune's rings have curious bright clumps called arcs, where material seems to be concentrated. The most prominent arcs are in the Adam's ring, the outermost of Neptune's main rings. The reason for these arcs' existence is still debated, but they may be caused by gravitational interactions with Neptune's moon Galatea. One of Neptune's most interesting moons is Triton, the seventh largest moon in the solar system. Triton is unusual because it orbits Neptune in a retrograde direction, opposite to the planet's rotation. This suggests Triton didn't form with Neptune but was captured from the Kuiper belt. Triton is geologically active, with nitrogen geysers that erupt from its surface. It's also one of the coldest objects in the solar system, with surface temperatures around -235 degrees Celsius. If appearing at Neptune without a spacesuit is deadly, appearing on Triton would be equally lethal, with the combination of extreme cold, lack of atmosphere, and no oxygen killing you within a similar time frame to Mars. But we're focused on Neptune itself, and the verdict is clear: survival time at Neptune is roughly the same as at the other giant planets. 1 minute until unconsciousness, 2 to 3 minutes until death. The extreme cold and powerful winds make Neptune perhaps slightly more immediately hostile than Jupiter or Saturn, but the difference is marginal. All the giant planets kill quickly through a combination of crushing pressure, extreme temperatures, and lack of breathable atmosphere. From Neptune, we've reached the edge of the major planets. Beyond lie the dwarf planets like Pluto, the Kuiper belt objects, and eventually the Oort cloud at the far reaches of the Sun's gravitational influence. But for our purposes, we've surveyed all 8 major planets. Now let's step back and compare what we've learned. We've taken a tour through our solar system's major planets, and the picture that emerges is sobering. Every world except Earth is immediately and profoundly hostile to unprotected human life. But the timelines and mechanisms of death vary significantly, and comparing them, Neptune and Uranus, being colder at their 1 bar levels, might incapacitate you slightly faster through hypothermia. Neptune's extreme winds would add violent tumbling to your final moments. Jupiter and Saturn, being warmer at their 1 bar levels but having higher gravity that makes you fall faster into higher pressure regions, might crush you slightly faster. But these are minor variations. The truth is that all 4 giant planets will kill you in about the same amount of time. And then there's Earth. On Earth, you can survive indefinitely, limited only by your need for food, water, and shelter. Even in Earth's harshest environments, survival is measured in hours to days, not seconds or minutes. Earth is the overwhelming outlier, the one planet where the environment actively supports life rather than actively trying to end it. Looking at these comparisons, several patterns emerge. First, atmosphere matters immensely, but in complex ways. Too little atmosphere, as on Mercury and Mars, means you can't breathe and pressure is too low to prevent embolism. Too much atmosphere, as on Venus and the giant planets, means crushing pressure. The composition matters too. Even if Mars had adequate pressure, its carbon dioxide atmosphere would still be unbreathable and toxic. Second, temperature extremes can kill, but they're often not the limiting factor. On Venus, the heat would kill you, but the pressure would crush you even faster. On Mercury, if you could somehow breathe, the temperature would eventually kill you, but the vacuum gets you first. On the giant planets, the cold is severe, but hypoxia claims you before hypothermia can. Only in scenarios where pressure and atmosphere are somewhat manageable does temperature become the primary concern. Third, the giant planets, despite their diversity in size, composition, and distance from the Sun, are all roughly equally lethal to humans on the relevant timescales. Whether you're on Jupiter at -150 degrees Celsius or Neptune at -218 degrees Celsius doesn't matter much when you're losing consciousness in 1 minute either way. Fourth, our solar system becomes generally more hostile the farther you get from Earth's orbital radius. Mercury, closer to the Sun, is more survivable than Venus. Mars, farther from the Sun, offers longer survival than Venus despite being colder. But the giant planets, much farther still, are not more survivable than Mars. They're roughly equal because their massive atmospheres create crushing pressure that Mars lacks. This comparison also highlights how special Earth's conditions are. We exist in a narrow band of temperature where water is liquid, with an atmosphere that provides the right pressure and the right composition at the right distance from the Sun to receive adequate but not excessive energy. The probability of finding another planet with such conditions seems low when you see how easily planetary environments can go wrong in so many different ways. The comparison also reveals something about planetary diversity. Venus and Earth are similar in size and mass, yet their surface conditions couldn't be more different. Jupiter and Saturn are both gas giants, yet they have different wind patterns and internal heat generation. Uranus and Neptune are both ice giants at similar distances from the Sun, yet Neptune is far more dynamic and generates more internal heat. This diversity reminds us that planets are complex systems where many factors interact to create the final environment we observe. Finally, these comparisons underscore the challenges facing human space exploration. Mars, the most frequently proposed target for human missions, would still kill an unprotected human in 2 to 3 minutes. Every human mission to Mars will require extensive life support systems, pressurized habitats, and spacesuits for any surface activity. The margin for error is slim. A suit puncture, a habitat breach, or a life support failure would give astronauts only minutes to respond before conditions became fatal. With this comparative understanding in mind, let's delve deeper into the science of human survival limits to better understand what our bodies can and can't tolerate. To truly understand why the planets kill us in the ways they do, we need to explore the limits of human physiology. Our bodies are remarkably resilient in many ways, capable of adapting to different climates, altitudes, and conditions. But there are hard boundaries beyond which our biochemistry and structure simply cannot function. Let's start with oxygen, the most immediate survival need. The human brain requires a constant supply of oxygen to function. Brain cells, neurons, are extraordinarily energy hungry, consuming about 20% of the body's total oxygen supply, despite the brain representing only about 2% of body mass. This energy is used to maintain the electrical and chemical gradients that allow neurons to fire and communicate. When oxygen is cut off, neurons begin to suffer almost immediately. Within 5 to 10 seconds without oxygen, you'll begin to experience impaired judgment and confusion as neurons start to misfire. By 10 to 15 seconds, you'll lose consciousness as the neurons controlling wakefulness shut down. The brain can survive without oxygen for about 4 to 6 minutes before irreversible damage occurs. Beyond 6 minutes without oxygen, brain death becomes increasingly likely. This timeline explains why so many of our planetary survival times cluster around the 1 to 3 minute mark. Once you stop breathing oxygen, whether because there's no atmosphere like on Mercury, a poisonous atmosphere like on Mars, or crushing pressure that prevents breathing like on the giant planets, you have about 1 minute until unconsciousness and potentially a couple more minutes before death is inevitable. Interestingly, the human body has some oxygen exhale rather than try to hold your breath. If you hold your breath during rapid decompression, the air in your lungs expands and can rupture lung tissue, causing pneumothorax where air leaks into the chest cavity, collapsing the lungs. By exhaling, you allow the air to escape naturally without causing this rupture. Radiation is another survival limit worth discussing, though it doesn't come into play on the timescales we're considering for planetary survival. Humans can tolerate low levels of ionizing radiation without immediate effect. We're constantly exposed to background radiation from cosmic rays, radon gas, and radioactive elements in the Earth itself. This background radiation amounts to a few millisieverts per year on average. Acute radiation exposure becomes dangerous at higher doses. Around 1 sievert of radiation received in a short time will cause radiation sickness, with symptoms like nausea and fatigue. 4 to 5 sieverts has about a 50% fatality rate without medical treatment. Above 10 sieverts, survival is unlikely even with treatment. These effects take hours to days to manifest, which is why radiation isn't a factor in our planetary survival scenarios. You'd be dead from other causes long before radiation could harm you. However, radiation is an important consideration for any long-term space travel or planetary colonization. Mars, for instance, has much higher surface radiation than Earth, about 0.25 sieverts per year compared to Earth's 0.03 sieverts. Over time, this elevated radiation would increase cancer risk. Jupiter's radiation environment is even more intense, particularly near the inner moons. Europa, one of Jupiter's most intriguing moons due to its subsurface ocean, receives about 5.4 sieverts per day on its surface, which would be fatal within weeks. Gravity also affects human physiology, though not on the short time scales relevant to our planetary scenarios. Humans adapt to microgravity during spaceflight, but the adaptations include bone density loss, muscle atrophy, fluid shifts toward the head, and vision changes. Conversely, in higher gravity environments like Jupiter's 2.5 times Earth gravity, your body weight would increase proportionally, making movement more difficult and placing more strain on the cardiovascular system. Over time, this might cause health problems, but in the short term, you could function, albeit with difficulty. The human body also needs water, but dehydration occurs over hours to days, not minutes. In our planetary scenarios, you'd die from other causes long before dehydration could harm you. Similarly, humans need food for energy, but starvation takes weeks. These slower-acting needs are irrelevant when survival is measured in seconds to minutes. One fascinating aspect of human survival research comes from historical accidents and near misses. The 1966 incident at NASA, where technician Jim LeBlanc was exposed to near vacuum conditions, provided valuable, albeit terrifying, data. He lost consciousness in about 14 seconds and was repressurized within another 15 seconds. He survived without lasting injury, confirming that brief vacuum exposure is survivable if pressure is restored quickly. In 1971, the Soviet Soyuz 11 mission ended tragically when a valve opened during descent, depressurizing the crew cabin. The 3 cosmonauts died within about 1 minute from the lack of pressure and oxygen. This incident highlighted the dangers of depressurization and led to changes in spacecraft design and procedures. Animal experiments in the 1950s and 1960s exposed dogs and chimpanzees to vacuum chambers to study the effects. These experiments, while ethically questionable by today's standards, confirmed that brief exposures to vacuum, up to about 90 seconds, were survivable with rapid repressurization and medical care. Beyond 90 seconds, survival became increasingly unlikely, and beyond 2 minutes, fatal damage was almost certain. These real-world examples align with our planetary survival estimates. Whether you're on Mercury, Mars, or falling through a giant planet's atmosphere, the timeline to unconsciousness is about 1 minute, and the timeline to irreversible death is 2 to 3 minutes. The specific mechanism varies: embolism, crushing pressure, hypothermia, but the fundamental limitation is the same. The human body requires oxygen, adequate pressure, and moderate temperatures to function, and it has very limited reserves when these needs aren't met. Understanding these limits helps us appreciate not just why space exploration is difficult, but why Earth is so precious. Our planet provides, without any technological assistance, everything our bodies need to survive. The atmosphere delivers oxygen at the right pressure, the temperature range supports liquid water and enzymatic reactions, and the magnetic field and atmosphere shield us from harmful radiation. On every other planet, multiple factors work against survival, and on some, like Venus, the environment is so extreme that even our best technology struggles to function there for more than a few hours. As we reach the conclusion of our journey, let's reflect on what these hostile worlds tell us about Earth, about planetary science, and about the future of human space exploration. We've completed our tour of the solar system's planets, and if there's one overwhelming conclusion, it's this: space is extraordinarily hostile to human life, and Earth is an almost miraculous exception. Every world we've visited, from scorched Mercury to frozen Neptune, would kill an unprotected human in timescales ranging from effectively instantaneous to a few minutes at most. Venus crushes and cooks you in less than a second, with its 92 atmospheres of pressure and temperatures exceeding 460 degrees. Mercury, depending on where you land, burns or freezes you, while the vacuum of space causes ebulism and asphyxiation, giving you perhaps 2 minutes at most. Mars, often portrayed as humanity's next home, would trigger ebulism and asphyxiation within 2 to 3 minutes. The giant planets, Jupiter, Saturn, Uranus, and Neptune, would each render you unconscious within 1 minute and dead within 2 to 3 as you fall through their crushing atmospheres and freeze or are buffeted by the fastest winds in the solar system. And yet, Earth. On Earth, you can step outside without any protective equipment and live your entire life. The air provides oxygen at exactly the right pressure. The temperature, while varying with season and location, stays within a range compatible with life. Water exists in all 3 phases, cycling through the atmosphere and shaping our climate. The magnetic field shields us from radiation. The biosphere provides food and maintains the atmospheric composition we depend on. This dramatic contrast between Earth and every other planet highlights several important themes. First, it underscores the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life suggested by the vast number of stars and planets and the lack of evidence for such life. If our solar system is representative, most planets are hostile to life. Even Mars, the most Earth-like planet in our system, is profoundly inhospitable. This suggests that planets with conditions suitable for life might be rare, or that life itself is rare, or that intelligent technological civilizations are rare or short-lived. Second, our tour highlights how many factors must align for a planet to be habitable. You need the right distance from the star, the right atmospheric composition and pressure, the right temperature range, liquid water, protection from radiation, and geological activity to recycle materials and regulate climate over long time scales. Venus and Earth are similar in size and composition, yet Venus went down a very different path, developing a runaway greenhouse effect that made it hellish. Mars likely had more Earth-like conditions billions of years ago, but lost its atmosphere and dried out. Small changes in initial conditions or evolution can lead to dramatically different outcomes. Third, these hostile environments remind us of the challenges facing space exploration. Every human mission beyond Earth requires carrying a piece of Earth with us: breathable air, water, appropriate pressure, and temperature control. These life support systems are complex, expensive, and can fail. The margin for error is slim. A suit puncture on Mars gives you 2 to 3 minutes to respond. A habitat breach could be catastrophic. As we plan missions to the Moon, Mars, and potentially beyond, we must respect the extreme hostility of these environments. But there's also wonder in this hostility. Each planet tells a story of formation, evolution, and the physical laws that govern planetary systems. Jupiter's storm systems reveal insights into atmospheric dynamics that help us understand weather on Earth. Venus's runaway greenhouse effect is a cautionary tale about climate change. Mars's lost habitability teaches us about planetary evolution and the factors that sustain or destroy conditions suitable for life. The giant planets, with their lack of solid surfaces and their crushing atmospheres, show us what happens when a planet accumulates massive amounts of hydrogen and helium during formation. They're natural laboratories for studying matter under extreme pressure and temperature, conditions we can barely replicate on Earth. The transition to metallic hydrogen deep within Jupiter and Saturn, the mysterious heat generation on Neptune, the bizarre tilted magnetic fields of Uranus and Neptune, all of these features expand our understanding of planetary science. Our descendants might one day walk on Mars, protected by advanced spacesuits and living in pressurized habitats. They might mine asteroids for resources or establish research stations on the moons of Jupiter or Saturn, studying these worlds up close. But they'll always be visitors in hostile territory, dependent on technology to create tiny bubbles of Earth-like conditions in environments that want to kill them. This makes our responsibility to Earth all the more profound. We live on the only known planet where life not only exists, but thrives. We're part of a complex biosphere that has evolved over billions of years, a web of interconnected species and ecosystems that maintain the very conditions we depend on. The oxygen we breathe is produced by photosynthetic organisms. The climate is regulated in part by biological processes. We are not separate from Earth's environment, we are deeply embedded in it. When we look at Venus's toxic greenhouse, or Mars's frozen desert, or Jupiter's crushing storms, we see what planets look like when they're not teeming with life. Earth's vibrant blue and green appearance from space, the swirling white clouds, the contrast between land and sea, this is what a living planet looks like. We are, as Carl Sagan memorably described it, living on a pale blue dot, a tiny world suspended in a sunbeam, the only home we've ever known. Our journey tonight through the solar system has been a tour of death, cataloging the ways each planet would kill us. But it's also been a celebration of life, a reminder of how extraordinary it is that we exist at all, on this one planet where the conditions are just right. Every breath you take contains oxygen produced by ancient cyanobacteria and modern plants. Every drink of water comes from a hydrological cycle powered by the sun. Every comfortable moment outside is possible because Earth's atmosphere provides the right pressure, the right composition, and the right temperature. So the next time you step outside and feel the breeze, see the clouds drift by, or simply breathe easily without thinking about it, remember, you're experiencing something unique in